What is electromagnetic radiation? I wanted to make a brief video on this topic here in the chemistry playlist because we're about to study the electronic structure of atoms. And as you may already be familiar with, this is based on the quantum numbers of electrons, quantum being directly related to quantum physics. And so to study the electronic structure of atoms, we're going to need to do a brief overview of quantum mechanics. The origin of quantum mechanics comes from studies that were being done on light or electromagnetic radiation. And so before we get into the history and basics of quantum mechanics, I want to make sure you have a solid understanding of what exactly electromagnetic radiation is. Here's a fundamental look at an electromagnetic wave. It's an oscillating electric and magnetic field that's propagating through space. So here you can see this is the oscillating electric field, and then perpendicular to that is the oscillating magnetic field, and it's traveling with a certain speed through space in a certain direction. Okay, but electromagnetic waves do have a special property that other waves you might be familiar with, like water waves or sound waves, don't have. These waves can propagate through empty space. If you think about a water wave, well, you need water. You need the water. In a sound wave, same idea, you need the air. A sound wave, you make a disturbance, and that pressure disturbance propagates through the air molecules. Or sound can travel through water or some other material, same idea. But an electromagnetic wave doesn't need a medium. For example, radiation travels from the sun through empty space to Earth. So where do electromagnetic waves come from? Well, we're going to get into more specifics on this in a second, but in general, an electromagnetic wave is emitted by an electron when it's accelerating or decelerating. Really, any accelerating charge, so a proton as well. But in general, we think about accelerating electrons because electric currents are from electrons. Electrons surround the nucleus. They're constantly in motion around the nucleus, which is relatively still. So we'll talk about the different places that electromagnetic radiation comes from in a second. But first, so electromagnetic waves can differ in one way. So, okay, all electromagnetic waves are propagating through space at a certain speed. This speed is constant for all electromagnetic waves. That's the speed of light, so approximately 3.0 times 10 to the 8th meters per second. Now, depending on the medium, this speed can change very slightly, but it's not much. So in general, the speed of light is constant. Okay? So the speed is constant, but the one way that electromagnetic waves can be different is that they can have different frequencies. Here's the range of frequencies of light or radiation, at least the range that we're currently aware of or have detected. I'm not sure if there's a proof that this is literally all of the possible frequencies that can exist, or maybe we haven't discovered any other frequencies. I'm not sure. But what this frequency is referring to is the frequency of the wave here. So we start here, we get to this point, that's one cycle. Same with the magnetic field. That's a cycle. So if we have a frequency of 10 hertz, that means that this is propagating through space with these electric and magnetic fields oscillating at a frequency of 10 cycles per second. Okay, now we also have wavelength here, but the frequency and the wavelength are sort of dependent on one another. Once you set the frequency, you've set the wavelength. In fact, so we can say that the speed of the wave is equal to the wavelength times the frequency. Wavelength is, let's say, in meters. Frequency is 1/seconds, meters per second. Well, the speed is constant. So again, you can see how once you set the frequency, you've automatically set the wavelength because C is constant. Now, another thing to point out here is how is the energy going to change as you move across this spectrum here? This is the electromagnetic spectrum. Well, the speed isn't changing. So if the frequency is going up but the speed isn't changing, then as the frequency goes up, the wave is going to have higher energy. So think about that. It's because the speed is the same in all cases. Okay, so again, this chart here is called the electromagnetic spectrum. It shows all of the different possible frequencies of electromagnetic waves. And based on these frequencies, or in a similar way, based on the wavelengths, it gives the name of the wave. So these longer wavelength, lower energy waves are called radio waves. Then we have microwaves, then infrared. This is the small range of frequencies or wavelengths of light that we can see. Okay, then shorter wavelengths, higher frequencies, higher energy. We have ultraviolet, then X-rays, then gamma rays. This is the highest energy. Okay, so where do these waves come from? Okay, so we'll start with this infrared visible kind of ultraviolet range. Okay, so here is the emission spectrum of the sun. The emission spectrum meaning, so we've got an intensity of radiation here, and then as a function of wavelength. And so here's the curve, and you've got the yellow and the red together. That's all of the radiation coming from the sun. And then the red is just what reaches sea level. So all of this yellow doesn't get through the atmosphere. Now, the first thing I want you to think about is whether you're an evolutionist or a creationist or some mixture of both. I think we all agree that light and the sun was there first before life. So in general, this emission spectrum was there before life evolved or was created. So in other words, life adapted to this emission spectrum. Okay, now if you compare these wavelengths to the wavelengths on the spectrum, what you'll notice is that, so the sun is emitting all wavelengths of light, all frequencies of light on the entire spectrum. Radio waves all the way up to gamma rays. But only shown on this chart here is from about here to here. The reason is because, yes, radio waves are being emitted and X-rays and gamma rays, but the intensity is low compared to visible light, infrared light, and ultraviolet light. And furthermore, in this range here is visible light. So the highest intensity, not the highest overall amount, but the highest intensity is visible light, which is why we evolved or were created to see with these frequencies of light. Now you might say, why wouldn't we evolve to see with the more abundant? You know, this area here is more than this area. Well, I think about it like with the more intense light, it's brighter. We have more of a range we can see. Okay, now thermal energy, which comes from the random motion vibrations of the atoms and molecules of any substance or any solid, liquid, or gas body, right? The extent of this motion, this thermal energy, is proportional to the temperature. Heat can be transmitted through direct contact, conduction, through a fluid like a liquid or gas via convection, or by radiation. So that's what we're talking about here. This thermal radiation comes from when the electrons that make up a body jump from a higher energy orbital to a lower energy orbital. They give off electromagnetic radiation. They can absorb heat radiation, so they move up to a higher energy orbital, and then when they jump back down, they give off electromagnetic radiation. But not just any electromagnetic wave is absorbed by an electron in this scenario and then emitted in the scenario of the electron changing energy orbitals. For example, we don't absorb radio waves. Why not? Because compared to the size of an electron or of molecules or atoms, radio waves are huge. It's a similar idea that when you're swimming in the ocean, you don't absorb the water waves. They just pass right through you, like you're not even there. The main frequency of waves that are going to be absorbed and transmitted in this process that causes electrons to jump around, that causes motion of atoms and molecules, random motion, is in this infrared range, and to some extent even visible and ultraviolet, but much more in the infrared range. Now, what about microwaves? Don't microwaves heat up bodies that contain water? And humans are made up, a large percentage of humans is made up of water. Well, this is a different kind of process. The microwaves are causing the water molecules to vibrate. It's a unique way that they interact with the water molecules. So microwaves indirectly cause something that contains water to heat up. Now you might ask, why don't the microwaves that do enter the atmosphere heat us up? We do use some microwave frequencies for communication, like police radar and satellites. Why don't those heat us up? Because the power level or intensity of microwaves that enter the atmosphere and that are used for communication are negligible compared to what's inside a microwave oven. So microwaves use power in the kilowatt range to cook food. Ultraviolet, one thing that comes to mind with UV rays is sunburns. But in that case, the electromagnetic waves aren't being converted to thermal energy. Same idea with like X-rays and gamma rays. Gamma rays are associated with radioactive decay. So like the harmful radiation, nuclear power plant type radiation. The human body can absorb these, but it's typically not being absorbed as heat. It's damaging cells, things like that. Now, yes, small amounts of gamma rays or X-rays could potentially cause harm, but just remember, even though some amount of this type of radiation is reaching Earth from the sun, but again, not even that much relative to visible light, IR, and UV light, right? Because this main curve here is radiation directly from the sun before it even gets to Earth. But once it gets to Earth, the atmosphere absorbs a lot of the harmful radiation, or maybe even all of it. And also, Earth's magnetic field deflects a lot. That's why you'll hear that without the atmosphere or Earth's magnetic field to protect us from harmful frequencies of radiation from the sun, we wouldn't survive. Similar idea with X-rays. So this spectrum here is the majority of the radiation around you when you go outside. But we do artificially generate radio waves with transmitters, and they're received with antennas. We artificially generate microwaves, obviously in microwave ovens, for example. We artificially generate X-rays. So here's an X-ray tube, an X-ray gun. Electrons are accelerated by high voltage, and they're brought to an abrupt stop here at the cathode. When they decelerate to an abrupt stop very aggressively, they emit X-rays. And then gamma rays are extremely high energy electromagnetic radiation. That's why they're so dangerous. They occur naturally in radioactive materials from the natural decay of the nucleus. In radioactive decay, you have alpha radiation, beta radiation, gamma radiation, and also neutron emission. But beta radiation, alpha radiation, and neutron emission, they have the term radiation, but they aren't a technical form of electromagnetic radiation. It's just a name that's stuck based on how these were developed. Alpha radiation is the emission of 2 protons and 2 neutrons. Beta radiation is the emission of an electron, and then neutron emission is the emission of a neutron. Only gamma radiation is an electromagnetic wave being emitted from the nucleus due to radioactive decay. Again, these names are just based on how this was developed. At the time, they detected radiation coming from the nucleus, high energy radiation, and they didn't know what was a particle and what wasn't a particle, so they just termed everything as radiation, and the names stuck. But one thing you can think about is this is dangerous because it's such high energy. But let's say hypothetically radio waves were also extremely high energy. Well, we don't absorb them. So they're dangerous because they're high energy, but also because components in human cells absorb them. So radio waves, AM, FM frequencies, television, cell phones, Wi-Fi. So obviously the Wi-Fi signal in your home can penetrate the walls, but they're not as long as radio waves. So you can't go too far from your modem, or else you start to lose signal. Microwaves, microwave ovens, police radar, satellite stations. Here's heat lamps, so sun tanning, and obviously X-rays. But again, the most abundant electromagnetic radiation that we get from the sun, which permeates the atmosphere and reaches Earth's surface, is IR radiation, also with some visible light and UV radiation. Now, you can think about visible light to some extent being absorbed as heat. So you wear a black shirt versus a white shirt. The black shirt absorbs more radiation, and a similar idea with UV rays. But in general, for the most part, the waves that are being absorbed as heat, so causing the electrons to jump from orbital to orbital, absorb radiation, jump up, jump back down, emit radiation. This is in the IR spectrum. If we could see infrared waves, then this would be much clearer. For example, here's an infrared image. The warmer skin of the body is emitting more infrared radiation than other objects at room temperature here. Any object or any body, any solid, liquid, or gas body that's above absolute zero temperature, so above 0 Kelvin or 0 Rankine, is going to be emitting some amount of thermal radiation or infrared radiation. Again, from those electrons jumping around the orbitals. When it's cold, we obviously can't see the infrared radiation being emitted. All we can see is the visible light being reflected. Okay, now what about the term black body? What is a black body? Well, the first thing you need to understand is that there's two scenarios. First, if you have a gas, any gas that's at a very low pressure, so meaning that you have a very low pressure, thin amount of gas, low number of molecules, and if you heat that up or run an electric current through it to heat it up, and you capture the radiation it's emitting, with things like prisms, you can separate out the different frequencies. You'll get a discrete spectrum, like shown here. Discrete frequencies of light. This, for example, is neon, so neon gas. But if you do this with a regular gas at regular pressure, or with a liquid body or a solid body, you don't get a discrete spectrum, you get a continuous spectrum. For example, like from the sun, there's not only certain frequencies being emitted, in general it's all frequencies. It's a continuous spectrum. But like even if it wasn't all frequencies, you could still think about the idea of continuous spectrum for like a certain range of frequencies. But coming back to the sun, effectively the sun emits a continuous spectrum of all wavelengths of light. So that's the idea of a black body. It's a perfect absorber of all wavelengths of light. It doesn't transmit or reflect any light. It's an ideal absorber of all light. And then by the first law, because it's an ideal absorber, that also means that it's an ideal emitter. It emits all frequencies of light. Now, a phenomenon of black bodies is that all black bodies, solid, liquid, gas, any material, has an emission spectrum like this that's only dependent on the temperature. You can see how the curve changes just as a function of temperature. So again, the state doesn't matter, solid, liquid, or gas, and the type of material doesn't matter as well. The only thing that matters is the temperature. All black bodies will have emission curves like shown here that are just dependent on the temperature of that body. So stars are known as black bodies. All stars, like the sun, for example. Notice how the sun's emission spectrum follows that black body distribution at a certain temperature. Something like this. The sun is about at 5,800 Kelvin. But it's not just stars that act as black bodies. Any solid, liquid, or gas body on Earth or in the universe can potentially act as a black body. So, for example, charcoal acts like a black body, certain metals. And if it's not a black body, and there's no such thing as a truly black body, so a real body at a certain temperature, the emission spectrum of that real body is just going to be a deviation from this black body curve. So again, unless you have like a low pressure gas where you're just dealing with, in some sense, one atom or molecule at a time, in those cases, the gas is emitting a discrete spectrum. In all other cases, just general solid, liquid, or gas bodies, you're going to have some sort of continuous spectrum, some sort of deviation from this black body curve at the respective temperature. But just focusing on black bodies at the moment, what you notice is that as the temperature of the body goes up, and again, no matter what the size of the body is, the type of material, the state, solid, liquid, or gas, the black body emission spectrum is the same, only a function of the temperature. But as the temperature goes up, you get a larger portion of the emission spectrum being visible light. And as the temperature gets higher and higher, even the peak intensity range is in the visible light range. Now, as the temperature goes up, the amount of infrared radiation is also increasing. So in all cases, the largest area is coming from the infrared spectrum. But still, as you get to high temperatures, you do get a more significant portion of the area being in the visible spectrum, but the peak intensity does come from the visible spectrum. And this is why if you heat up certain pieces of metal that act as black bodies, or even a metal that doesn't necessarily act as a black body, because in a lot of cases it's just a certain fundamental deviation from this curve, but it's still behaving in a similar way as a black body, you get red hot, then yellow hot, then white hot, which is like, kind of a combination of all of the colors, and then blue hot and purple hot. So for example, the sun is a relatively lower temperature black body than other stars. The sun is like a yellow hot, but there's other stars that are blue hot, blue stars. These stars are hotter than the sun. But here's a piece of metal that's at like a yellow, orange hot, and also white hot in some regions. But on Earth, at room temperature range, or even on a hot summer day, or the coldest of winters, kind of those temperature ranges, solid, liquid, and gas bodies around us are at lower temperatures than what's shown on this graph. So room temperature is about 295, 300 Kelvin. And so what you can notice here is that when we get to more room temperature ranges, the visible light and UV spectrum is almost cut off, right? So that's why at night, when there's no visible light coming from the sun, or without flames from a fire or light bulbs, both of which are heated to glowing hot, where they're emitting visible light, we can't see anything because everything's just emitting purely infrared radiation. But also notice that it's not like if you can see infrared or with an infrared camera, if you went to Antarctica and put on an infrared goggles, you'd see everything glowing, because at lower temperatures, the total radiation in general, even with infrared, is going down. But if any object or body is above 0 Kelvin, it does have an emission spectrum, which again is going to be dominated by the IR spectrum. Now you might be asking yourself, well, okay, here this is like a mixture of a glowing orange, yellow, white. The sun is also like glowing white or orange-ish, yellowish. Same with like certain light bulbs, glowing white light. So objects like this must be close to the same temperature as the sun. Well, no, the sun is much hotter than this piece of metal or the filament in a light bulb. Correlating color to temperature is not as simple as just looking at the color. For one, you can see that, so the filament in a light bulb, well, first of all, this looks white, but you could also argue that it's kind of a reddish white, orangish white. This filament here is about at 3200 Kelvin. So around here, well, this is still giving out a good bit of all forms of light. So, it's kind of a white light coming from the light bulb. But when you get to the temperature of the sun, so the sun is about at 6,000 Kelvin. Let's look at this 5,000 Kelvin. This is also going to be kind of a white light, but a little bit more white, more yellowish perhaps than reddish white. But it's going to be more intense, right? It's going to be brighter. But even more than that, there's more complicating factors. With the sun, it depends on the time of day. You could have, the sun is sometimes more of a bluish light coming in. Not blue like this, like a rich blue, but more bluish, depending on the time of day. And then stars are also complicated because there's different layers of stars. We only see the photosphere, but there's different layers of stars that are at significantly different temperatures. So with a star, it's not the same thing as looking at a piece of glowing metal. There's no layers to this metal. It's just one glowing piece. Okay, so at room temperature or even really cold temperatures, but typical scenarios on Earth, without visible light from the sun or from lamps or light bulbs that are glowing hot, to detect the electromagnetic radiation coming off of bodies around you, you need to be able to see infrared, like shown here. So in general, an infrared camera is just detecting bodies that have more infrared radiation coming off of them and mapping those bodies to be more red and the ones with less, more blue. However, if you have an infrared camera that's also reporting temperatures, or maybe it's not even reporting temperatures, but it's scaled to temperatures, then it's not quite that simple, because the software needs to consider how much the body reflects, absorbs, things like that. But in general, that's the idea. It's just detecting the amount of infrared radiation coming off the body. Now, you might be wondering, well, why are the hotter regions red and the bluer regions cold? We just talked about, red hot's colder than blue hot. That's just convention. So the software writers could program this however they want. They could make hotter regions blue and cooler regions red. This is just programming. This has more to do with our experience on Earth. We think, as humans, we think red, hot, blue, cold, because we don't live at temperatures of stars and glowing objects. Now, what's interesting to notice here is that This picture here is the picture taken by this person, but this is an image from the IR camera. So why are we seeing a reflection here? Well, it's all about the absorptive, reflective, and transmissive properties of this window at different frequencies of light. And later in the video, we're going to talk about this idea of how real bodies, actual solids, liquids, and gases interact with light differently at different wavelengths, different frequencies. So this window is transmitting visible light, so we can see through it. But it's reflecting a lot in the IR range. So for the IR camera, this window is like a mirror, but we see through the window. Okay, now there may be a few things that you still find confusing at this point that I want to clear up. First of all, when you think about a black body absorbing all frequencies of radiation, well, we talked about, depending on the size of the body, it might not absorb radio waves, let's say. Radio waves pass right over it. The idea is more of that, you can think about it like, so we know that any body is going to do one of three things with radiation, let's say that it interacts with. It's either going to transmit it, absorb it, or reflect it. And then we don't really talk about, well, what happens if it's like a radio wave that just passes right over it? That's not transmitting, reflecting, or absorbing it. So a black body, we're more talking about the electromagnetic waves that it interacts with. It doesn't reflect or transmit, it absorbs all of them, regardless of the angle the waves are coming in, of any factors other than, yes, if it's an enormous radio wave, it's obviously not absorbing it, but that it's still a black body. Okay, the next thing that could be confusing you is that, okay, so a black body absorbs all radiation it interacts with, and then because of the first law, since it absorbs all radiation, it also emits all radiation. And this is the emission spectrum of the black body depending on the temperature. Well, then in that case, this also must be like the absorption spectrum, right? No. If you think about it, there is no such thing as an absorption spectrum that's like unique for a material. The absorption spectrum's just depending on the environment something is in. You as a person, if you're outside in the sun, well, that's one potential absorption spectrum. If you're in a nuclear power plant, unprotected, that's another absorption spectrum, right? The spectrum that any given body is absorbing just depends on the radiation that's upon it at some moment. But the idea is, in general, regardless of the incoming radiation, a black body is going to have this emission spectrum. So if you're outside in the sun, yes, you'll have a different emission spectrum than if you're inside because your temperature is going to be different. Your temperature will be cooler, but you're going to have this same emission spectrum. You're going to have that same black body emission spectrum. Well, you as a human body will have some sort of a deviation from this, but just we're talking about black bodies for the sake of discussion right now. We'll get to non-black bodies in a second. And this might be a little confusing because you might be thinking, well, if I was unprotected in a nuclear power plant, well, you'd be dead soon, very quickly. But wouldn't I be, if I'm getting hit with gamma radiation, wouldn't I be emitting gamma radiation? No, because a lot of that gamma radiation you would absorb. It would damage the cells and then be converted to heat. But maybe not that much of it would be converted to heat because it's not like your temperature would rise. You'd be getting damaged, but your body heat wouldn't be rising, right? Like the sun has a lot of nuclear explosions going on inside of it, but a lot of that is getting converted to heat. I mean, and yes, depending on the circumstance, maybe for different bodies, there might be a bit more of the gamma radiation if you're in like a nuclear environment, but still the general curve is going to be the same. Just because this goes up a little bit doesn't mean the overall black body curve is not going to, in general, be the same. Okay, now there is no such thing as an actual black body. No actual black body exists. It's just an idealization that real bodies are compared to. Stars are examples of bodies that are very close to the idealization of a black body. They are emitting, and as a result of the conservation of energy, you can think about it as also absorbing all frequencies of radiation with no bias for one frequency or one range of frequencies for some reason. But most solid, liquid, or gas bodies that we interact with aren't black bodies. So how do we approach this? Well, you might see or hear statements such as solids absorb and emit continuous radiation, termed black body radiation. But that's obviously not technically true. For one, there's no such thing as an actual black body. But we know, for example, from charts like this is a chart for a window. You can see it's transmissive here in the visible range. But it's not a black body. It's not 100% absorptive over all wavelengths. solids or any regular body on Earth, solid, liquid, or gas body, so like the atmosphere, for example, just outside, will sometimes be referred to as black bodies because they are emitting that continuous spectrum, that non-discrete spectrum. Even though, as we just saw, the body may have an irregular absorption distribution curve over the wavelengths of light. But there are bodies, solid, liquid, or gas bodies, that behave very similarly to a black body in that they don't have any irregular absorption, reflection, or transmission patterns at different wavelengths. It's smooth all the way through, but it only absorbs a percentage of all of the radiation. So in other words, you take one of these curves and multiply the entire curve by a constant between 0 and 1 to scale it down. That's called a gray body. For example, some metals can be very reflective, so they obviously aren't absorbing all of the radiation, but they still behave very smoothly over all of the wavelengths of light as far as the absorption. So they're gray bodies. You just take the black body distribution and multiply it by what's called the emissivity. The entire distribution you multiply by the emissivity, let's say 0.3, and that's the distribution curve. Even if those metals aren't necessarily black, they may be reflecting a certain range of visible light, but still in general over all wavelengths, they behave smoothly. Materials might have reported absorptivity values, reflectivity, and transmittivity. The idea here is you could get the area under the curve for all frequencies of light for tau, alpha, and rho. The area under each curve relative to the total area gives a value between 0 and 1. The three values will add up to 1, but that's how you can get sort of an average absorption, transmission, and reflective property of a material. Or what you can do is you could get the relative areas for certain wavelength or frequency bands and report a tau, alpha, and rho for different frequency bands. So maybe from here to here, you would report the average tau, alpha, and rho, and then from here to here, you report a different one for this material. Now, coming back to the fundamental way that we described what light is, shown here, this oscillating electric and magnetic field propagating through space at the speed of light. Just looking at this, it seems like light is a ray. We call it a wave because of this wave-like nature, and it's propagating through space kind of like a particle, but really it's more of like a light ray. And Isaac Newton's theory on the nature of light was the prevailing theory until the start of the 19th century. Newton thought of light as small particles traveling in straight lines, so small particles of light traveling in straight lines. So not exactly a ray, but still makes sense with what we see here. But at the start of the 1800s, experiments were done that proved definitively that light, at least in some sense, behaved like a wave. So not like a wave as shown here, but like a wave in the sense of how we think of water waves, sound waves. They aren't rays or particles. They propagate as this continuous medium spread out in all directions. They can interfere with one another, produce interference patterns. So that just means whenever they cross over, they can reinforce each other and get larger, or kind of destruct each other or cancel each other out and get smaller, right? So if you pass a wave through a slit, it spreads out like this. If you pass a wave through two slits, then you can get these interference patterns where you'll have these, if you look at this from the front, from this direction, you'll have these bands of large amplitude where the wave has reinforced it and gotten larger in amplitude, but in the middle of that is these smaller bands of where it's a low valley, where the wave has canceled each other out. And so in the early 1800s, experiments were done that showed light behaved like a wave in this way. And intuitively, I think we sense this. It seems like light almost bends around corners. If you turn on a light in the kitchen and you're not in direct line of it, it's almost like the light spreads out and reaches you even though you're not in direct line of sight with the light, right? If it was just a ray, that wouldn't happen. But sometimes it is like you see a ray of light, isn't it? you see these light rays going through the air. And furthermore, experiments show, so if they do this experiment, this double slit experiment with light going through these two slits, but they do it with very sparse amounts of light at a time. So as low an intensity of light as they could possibly get at a time. This is what happens. It's like these particles of light or rays of light or particles of light that are hitting the screen. But, so you do it this way, but they keep the experiment going. They keep it going, keep it going. This is what eventually develops. You're still doing this entire process. You're doing this one like tiny little piece of light at a time. Like here, they didn't just all of a sudden turn on a large stream of light. They kept doing this from this picture all the way to this picture. They kept it at one tiny little piece of light at a time. So you've got almost like rays or little particles of light hitting the screen, but then it still develops that interference pattern like a full-on wave. Okay, so that's light. That's electromagnetic radiation. And throughout the 1800s, there was a lot of work being done to understand light, to understand electromagnetic radiation. One of the studies was analyzing blackbody radiation. So trying to understand this blackbody curve at different temperatures. They were trying to model it, come up with a curve fit for it. But you can't just come up with any arbitrary curve fit. You have to somehow explain your curve fit from a physics standpoint. Explain it in a way that makes intuitive sense to the scientists, as well as jives as much as possible with the existing science and any future science that comes in. There were formulas that could predict the short wavelengths well, but they would break down at longer wavelengths and vice versa. And it was in the development of a formula that could model this blackbody radiation accurately for all wavelengths that started quantum mechanics.